Good afternoon, everybody. Welcome to class today. Thank you for joining me. Whether you are watching live or you're watching the recording later on, I appreciate you watching. This is the very first time we've had a live stream this semester that's about the same module that you're in, right? And so it's actually because it's our last live stream. Next week we won't have a regular live class live stream as we normally do. I will try to have a kind of a drop-in Teams session during this time next week. So if you have questions about, stuff that you're working on for your final project, you can drop in and get assistance with that. Otherwise, this is the last live session, the last live time we're actually having a scheduled live class session for the semester. We're done. If you could remember back to late January, early February when we were getting started and we had all this work ahead of us, and now we're here at the end of the course and we're all relieved for it. Summer's just right around the corner, right? We have, roughly 1.5, 2 weeks left in this semester. So, it's pretty nice, right? Like, it's pretty nice to, have this almost over. And I know a lot of you have a lot on your plate over the next couple of weeks as well. So we want to just make sure that we're going to keep our head up. We're going to keep pushing forward, and we're going to finish strong, right? Because that's, that's always going to be good there. So we're finishing up talking about analyzing algorithms this week. What I'd like to do is just kind of focus on a couple of the different logic and data structures that we've used throughout the course of the semester. Talk about what kind of complexity they bring to the table, how we can kind of calculate complexity based on a situation, right? And then I'd like to end it with a big example where I'm going to use two different sorting algorithms to sort the same huge data set, so we can see just exactly what this means when I talk about the scaling of complexity and how time complexity is relative based on the data set and all that kind of fun stuff. And so last time we talked about what our different types of time are. We talked about constant time, O of 1, linear time, ON, logarithmic time, O of log n, exponential time, O of n squared. And we drew all these conclusions to what these different times were based on cakes and baking cakes for a party, right? Like we said, if we're gonna bake one cake to feed everybody at the party, then that's constant time. That's O1, right? Because it's the work's only being done one time, and it's going to satisfy the entire list of party guests, right? The entire set, as it were, for our problems. If we were going to kind of break it out into this like staggered tree-like structure, right, where the first person would get a cake, and the next 3 people, well, they might get 2 cakes, and then the next 5 people, they might get 3 cakes to split between them. Then that's logarithmic time, right? So that's the log of n. So we're kind of breaking things down, using time resources on different sizes of data sets to do kind of a similar thing. And that's going to save us a lot of time. Linear time being O of n squared, or linear time being O of n, rather, is 1 work for every object. So that means that every guest would get their own cake. O of n squared is exponential time. So not only would every guest get their own cake, but every guest's cake would have the names of every guest at the party written on their cake as well, right? So it's just furthering the work. And so the first thing that we want to look at here is a conditional. right? Because the idea of conditional sometimes confuse people, right? In terms of what exactly gets precedence as the most complex thing, or how we can calculate complexity through a condition. So when we're taking a condition, we kind of take it as its whole. But one of the things that we look at when we look at a condition, if we remember back to how a condition works in relation to what we've discussed throughout the semester, a condition only executes if that condition is true. Right? Otherwise, we have some other condition executing, or maybe we just have it moving on to the next thing. So when we look at complexity in relation to a conditional statement, a condition is only going to be as complex as its most complex part, as its worst case scenario. Right? Like if you guys will remember back to last week, we were talking about the idea of worst case scenario. And so if we're looking at the idea of like multiplying, or rather adding complexities, which if we looked at a conditional statement as a whole, we have two different sets of statements that might have two different complexities. And even if we were to take and chain our conditional statements, as we've talked about previously, with ifs and elifs and so on and so forth all down the line, only one of those things is going to trigger and execute the code. So if we were to look at our conditional statement as a whole, the complexity of this conditional statement is the most complex leg of the condition. Right? So if we had, say, one condition that was O of n, if it were to execute one condition that was O of 1, constant time, one condition that was O of log n, just these different complexities going down the line, whatever the most complex condition is the worst case scenario. So that becomes the complexity for that entire block of conditional code, right? Whether that code is run or not, it's only going to be that complex in the event that that condition is true. Right? But the worst case scenario is the slowest of all the possibilities. So if we look at this in terms of we have one statement that is, like we have in our example here, one statement that's O of 1, one statement that's O of n. In technical terms, we could write this because they're both kind of adding complexities to a block. So we might even look at it as like O of 1 plus O of n. But what's going to take precedence here, since we're not doing multiplication, right? We're just kind of doing these additions. And there are instances in which we would add certain things, but we're examining the complexity of the statement as a whole. So if we run a max function on the time it takes to run each block, we see that, O of n definitely takes longer. And so that becomes the worst case scenario for that set of conditional statements. And so that becomes the ideal, that becomes the complexity for that block. Loops, on the other hand. So loops are a nested data structure, or loops are a data structure that we've been using. Nested data structures on the next slide, just caught it out of the corner of my eye, which is why I started talking about that. But loops are a data structure that we've used. And, one of the ideas that we talked about last week was the idea of a loop having some number of items that it needs to traverse over, right? You know, we've talked about iteration, iterating over a list, iterating over, you know, different things. A while loop is basically just iterating to, you know, if we do like a while true, right, that's basically just iterating to infinity unless we introduce a break clause. We have some determined or yet to be determined set of values that we're iterating over for a loop. And so whether that set of values is 2, 5, 10, right, whatever, or if it's infinity, right, anywhere from, you know, 2 all the way to infinity, it's going to represent n items, right? So a loop is always going to add an O of n complexity to your programs. An O of n complexity to your programs. Because that loop is going to execute n times. And that is if the most complex statement inside of the loop is just constant time, O of n, or O of 1 rather. If everything inside of the loop is O of 1, then it's just going to be O of n. In an example that we're going to be doing a little bit later on, we're going to be doing an example of a merge sort. In a merge sort, we have a loop, or we actually have several loops, but you know, the most complex loop is the one that's going to take precedence, and every single loop individually is just O of n time, right? A loop on its own is O of n time as long as it doesn't contain another structure that's being looped over and over and over again that is more complex. But then it's also going to be recursed with a tree structure where we're going to be taking a list, breaking it down, breaking it, and just splitting it apart. You know, we'll look more at this in just a minute. But we'll split it in half. Then we'll split both the halves in half and all the halves in half again until we're just down to single item lists. And then we'll start reconstructing the original list in order. So since we're using this tree structure here, right, it's like we baked one cake here for these two. We're baking 2 cakes here for these 4. We're baking 4 cakes here for these 8, right? That's logarithmic time. Log n. O of log n. So when we get to our merge sort, we'll talk about how, since we have these two structures nested inside of one another, in that case, our merge sort would be O of n times the log of n. Right, so it all is dependent, you know, our loop is always going to be O of n as long as it does not have another structure inside of it or something else inside of it that is bringing about more complexity. Right, and in the case of our merge sort, we'll talk about it, it's a recursive call that's happening there. So the next thing that we have to talk about is our nested loops. And our nested loops will actually bring us to our first example. And so when we put a loop inside of a loop, it is dependent on the length of our lists. Right? We'll talk about a bubble sort here in just a couple minutes. And in talking about a bubble sort is a nested loop that is one loop inside of another loop, although the interior loop is one less than than the exterior loop. Right? And we just use this to compare numbers in a set, and it allows us to put things in order. Right? It's the most simple to write sorting algorithm, but it is one of the most complex sorting algorithms to in terms of processing time, right? Because it is, it's technically O of n times m, like we see it here, right? Because our exterior loop is one length and our interior loop is another length. So when we are looking at two loops that are distinctly different, that are inside of one another, we would consider that to be O n times m. However, our bubble sort actually meets the last sentence of our bullet point here. So when we look at it, we think, well, technically our bubble sort is O of n times m, because the interior loop is smaller than the exterior loop. But when we look at this last sentence here, in a common special case, bubble sort, where the stopping condition of the inner loop is j is less than n instead of j is less than m. The inner loop also executes n number of times. So in order to actually do our bubble sort, we have to stop at one short to be able to compare the last item, because there's nothing that comes after the last item that we can compare it with, but we still have to do n number of operations on the loop, which is fairly interesting. So what I'd like to do here, and in that case it makes the total complexity for the two loops O of n squared, because you're still running n operations n times through the loop. So it's n times n, which is n squared. And so what I'd like to do is I'd like to write a bubble sort for you all, just to show you how complex, to show you the complexity. Right? What I'm going to do here first is I'm going to start with a small data set, and then in a little bit I am going to increase that data set massively after we talk about a merged sort. So let me find my replit window here. And we'll start to write our bubble set, our bubble sort here. And actually what I'd like to do is I'd like to put our numbers here in an exterior window. Or an exterior file, rather. So I'm going to get on random.org. I'm going to go ahead and open the website here in another tab. And I'll bring it over. When I'm, teaching things like sorting and things like that, I love using random.org because they can provide me a good random number set. I'm going to go to random.org. I'm going to get an integer sequence generator, or an integer set generator here. I'm only going to want one set that has, let's say, 25 numbers between 10 and 99. So just to start with here, we're just going to keep it small, relatively small data set. Doesn't matter if we number the sets sequentially or not, so I'm going to uncheck that. I do want to use commas to separate the numbers because I don't want to have to manually go through and type all the commas in my list. However, I don't want the members of each set sorted in ascending order because I want to sort them myself. So I'm going to uncheck that box there, and I'm going to get my set. I don't think so. Well, I tell you what, since it wants to be, I will use some of the numbers out of my big data set for this. So let me just, I'm going to add a file here. I'm going to call it set.py. And, for a small data set, you don't necessarily have to do this. For the large data set that I will be using in a little bit, you're going to want to do this because I'm going to be sorting 10,000 numbers coming up here shortly. For the time being, I'm just going to sort that many. which I just took a small random subset there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13 numbers. Good enough to get us started. Right, we can see that they're all 5-digit numbers. When I generated my set of 10,000 random numbers, I generated them from the number 10,000 all the way up to 99,999. And we can see they're all out of order here, right? Like we start with the 99,000, go to 66,000, 39,000, 82,000, 23,000, 13,000, so on and so forth, right? All out of sorts. And so as we're programming here, we're going to program our way to be able to write a bubble sort. So I'm going to start off by adding my shebang, hashbang, /usr /bin /env python 3. And I'm going to import that set. So I want to be able to import set, and we'll give it an alias as s. Right, so now when we refer to that set, since we're referring to it out of another file, we will refer to it as s.numberset. Right, so if we were to just quickly, for proof of concept, print s.number_set, that pulls in our list from the previous file. And I might have had a little bit of desync here, so let me... Yeah, there we go. So see, we can see it pulling in our number set from our other file there. That's what we want. So I'm going to create a bubble sort algorithm, and our bubble sort is going to be able to sort these numbers. Bubble sort's a pretty simple algorithm to write. But again, in terms of time complexity, it's one of the worst. But it's going to be able to take these numbers, and it's going to be able to sort them and give them to us in a sorted order. With this small data set here, it's going to be relatively easy to do. We'll see what it's like when we get to our larger data set here in a few minutes. Right, so I'm going to define a bubble sort algorithm. We're going to bring in the array as a parameter, so I'll just call it R here. And we'll write our nested for loops here. So for I in range 0, the length of our array, and then for j in range 0, comma, the length of our array, minus 1. If r j is greater than the number that comes after it in the array, which would be r j plus 1, we want to be able to flip those, right? So we're going to take a temporary variable, set that equal to r j plus 1. We're going to take r j plus 1, set that equal to r j, and r j will be set equal to our temporary variable. Right, so we're just taking these two numbers and just swapping their places. Right, I have to store it in a temporary variable, because if I didn't store it in a temporary variable, we'd have it here. Actually, there's an interesting Python way to do it as I think of it, because I think in Python I can technically do this, which is fun and weird. I can say r j comma right. Oh, you know what? I don't want to confuse you all, so that's fine. But there is a way that we can declare multiple variables at once. So I can say that basically rj comma rj plus 1 equals rj plus 1 comma rj. I don't want to confuse you all, though. I want to make it nice and clear. So we'll just store things in a temporary variable here. until we go on, to the next thing. And so that's basically all we do, right? So each time through the loop, it's going to go through every number in the loop to make these comparisons. It's going to compare the one number to the next number. If the number that comes before the next number is larger than the next number in the set, it's going to switch them around. And that's going to give us our sorted list. And so now at the end of that, right, we can just return our sorted array. So behind our main gate, we can print the function bubble with s.numberset as the array parameter. Easy enough, right? So we see right now, we see here the unsorted array. We'll also have it in our set.py file, so we can go back and check it. If we run this now, we can see the sorted array. Now I want you to remember how quickly that happened, right? Because like when we pressed that, it stopped almost immediately. And this has a lot to do with the size of our set that we're using here. Right, the size of our set that we're using. What we'll see in just a few minutes, after we do our merge sort, is we'll see the complexity scale exponentially. Even in something that's relatively small, as in difference, as O of n squared compared to O of n times log n, right? We'll see a big difference there. So before we get to that, I'd like to just talk briefly about the idea of the invocation of a function. So when it comes to function invocation, essentially we're talking about the same thing that we were talking about with a conditional, right? If we're invoking a function inside of another block of code, it's going to add the complexity of that block of code or of that function to that block of code, right? So if the other function is more complex, it's going to bring its complexity back in the case of a conditional. In the case of a loop, it's going to multiply. Right? When a statement involves a function or some kind of procedure invocation, the complexity of that statement includes the complexity of the function. So, again, like if we're iterating over something, that's automatically going to be O of n. If inside of that function, if we call a function in there, and inside of that function call, we're iterating over the same list to do something else, that's also O of n, so we'd have O of n times O of n, which would be O of n squared. And so one of the places where we see that would be in use with recursion, and we use recursion in a bubble sort. Or not a bubble sort, a merge sort. I have a bubble sort in front of me right here. So what I'd like to do here is I'd like to write another function. We're going to leave our data set small for the time being. I'm going to write another function. And this is going to be for our merge sort. So we'll call it def merge. And just like with our bubble sort, we're going to bring in an array as a parameter. And so the first thing that we're going to want to do is we're going to want to keep running this until we get our starting list down to a single entity sized list. So as long as if the length of our array is greater than 1, we're going to do the following. Now eventually, looks like a little desync issue here. Eventually we'll get to the point where we'll have all of our arrays broken down into single entity arrays or single entity lists. In that case, we're basically done at that point, right? So we're not going to recurse this anymore. But we need to get our midpoint. So I'm going to bring in I'm going to calculate the number of values to get us to the middle, and put that in a variable. We'll call that variable mid. And so in order to do that, one of the things we could do, we could import our math library and do math.floor, length of array divided by 2. But there actually is a floor division operator built into Python. So we could just write the length of our array / 2. Single slash is regular division, double slash is floor division, which means it's going to round down to the nearest whole number. And so that gives us the midpoint of our starting list. And so what we're going to do is we're just going to split that off in that tree structure we were talking about earlier, right? So from our starting list, we're going to break that down into... So we have our starting list. We're going to break that down into 2 opposing lists. A left list and a right list. And then we're going to take that left list and break it down into 2 lists. A left list and a right list. The right list the same. It'll break down into a left list and a right list. And we'll keep doing that all the way until we have single entity lists. Whatever that may be, and then we start kind of putting things back together, going the opposite direction, right? So we see this tree structure here. And when we talked about, logarithmic time, that's what we're talking about. We have, in this instance, we have 1 cake. In this instance, we have, like some number of, So here, this is 1 cake. We have 2 cakes here, right? That operation and that operation. When we get to this part, 4. Even though we have different sets, different amounts of numbers, right? In this instance, we're using 1 work for all of that, 2 works for all of that, 4 works for all of that, so on and so forth. Logarithmic time. So in order to split my array, I'm going to use my my array splitting methods that we talked about earlier in the course. Right? So we're going to have left array equals array split to the middle, which would be colon mid. So remember, when we're starting that array, the colon represents, when we start with a colon without a number before it, that represents, up to, but not including the midpoint of the array. We could also represent it this way as well. Right, but if we have nothing before the colon, then it is implied. For our right array, we'd flip that around and say that's R mid to colon. When we don't put anything after the colon, that is implicit of it going to the end of the array. So that's everything from that middle number to the end of the array. And so now, since what that has done is take my array and split it in half, and what I want to do is I want to take my arrays and split them all until they're single entity arrays. Well, I want to split them in half again and split them in half again. So I'm going to make recursive calls here. Right? So we're going to call the merge function once with left array, and again with right array. And so these recursive calls will just keep splitting our arrays in half until we get to that point where we have a single item array. And so in order to deal with these arrays, what I want to do is I need some sort of iteration variables that I want to work with here. So I need to declare 3 variables here. We'll say I equals 0, j equals 0, k equals 0. And now I said, in addition to, kind of doing this split, which we're doing here, and we're doing it recursively, right? So that's O of log n. We need to use some loops here, and that's O of n, which is going to get us to O of n times log n. So I'm just going to write some while loops. While I is less than the length of the left array, and j is less than the length of the right array. Right, so we're doing things to both sides of the array at the same time, both the left and the right side of the array. What I want to do is I want to take the value at k in the primary array and set that equal to the left array at its current index location. So this is similar to kind of the way we were treating the temporary variables in our bubble sort there, right? So we have these 2 arrays split off, and they're in their own data. They're in their own arrays in their own variables now, right? So they're their own data structure. So now we can go back and manipulate the originating array and put it in order as we're putting it back together. By utilizing these other arrays. So it's kind of like using that same temporary value there. And from there, we're just going to increment I plus equals 1, right? To take me to my next item in my left array. And actually, I jumped the gun there. Because how do we know that we're in the right place in our array? We actually have to do the check. We have to say if left array index location I is less than right array index location j, right? Because we're only going to add the smaller of the 2 numbers to the array, and so then we can do that. Sorry about that, everybody. Kind of jumped the gun there. Else, it's flipped, right? So that would mean that RK becomes the right array J, and we would want to increment J to get to the next number in the J array, or in the right array. So else RK equals right array at index location J, and we're going to increment J to get to the next value in the right array, right? So essentially what we're saying here is while we are within the length of our arrays, and since an array can be an odd number in length, they could be different lengths, so we use our and operator here to check for both of them. So while we are both within the scope of our right array and our left array, we're going to check the values at our current location, right? And so if the value at the current location in the left array is less than the value at the current location in the right array, that's the value that we're going to take and put into the main array, because it's less. Otherwise, the right array value is going to be the one, and we're going to increment whichever array we put in the main array so we can get to the next number on that side of the array, just so we can see which one is next. Right, so now we just want to check to make sure that we have no numbers left in these arrays. So we'll say while I is less than length of the left array and this is just going to clear everything out, right? So in the event that we have one left over here from this array, we're starting a new while loop. As you can see here, their tab levels are on the same level. We're just going to put the last item from that array in the event that, you know, one side was smaller than, one side was smaller than the other, whichever one was longer. We're just going to make sure we get that accommodated back into the main array. So we're just going to say RK equals left array at index location I and we will increment the value of I and K. So that's I plus equals 1 and K plus equals 1. And we'll do the same thing for J and the right array. While J is less than the length of the right array. Goodness, this is a tongue twister. Then we will take that value, put it into RK. So RK equals right array at index location J, increment J, increment K, and that will make sure that we get everything out of those left and right arrays when we're done, right? So we have nothing in the left and right arrays, and everything is back into the main array sorted. And so from here, we're done, right? So we can just return. We can make sure we're, backspaced all the way back out, and we can return our array. And so if we look at this here, right, we have our tree structure here. That's going to give us log n. We have these different while loops down here, right? Remember that they're not nested while loops. They are on the same tab level, which means that the complexity is going to be reflexive of the most complex item, which is just O of n. So since we are doing this O of n every time we go through and split our array, this part is O of log n, this part is O of n. So since we're doing this every time we do this, because we are doing it recursively, we have to multiply the two together, which gives me O of n times log n, or O of log n times m, or n. So now we can see this in action, right? And we can take and we can call our merge sort on our number set, and we can run it. What did I miss? I'm going to have to go back and check my notes here, because that should be returning me my merged set. I had to make a little typo somewhere probably, or maybe it's stuck. So we will copy that and refresh first. Let's see here. Let me compare this to my notes. Mid is the length of array. That's right. That's good. That's good. I, J, and K. While I is less than len, left array, and J is less than len, right away. If left array is less than right array, we're putting that back in there. Else. That's what I missed. I need to increment K. K plus equals 1. There we go. Just like that, right? Something easy to miss, as to just skipping over the incrementation of K, right? So that is our merge sort algorithm there. And now we can see when we do that, it's pretty quick. It gives us it returns our sort fairly quickly. And so we can see this in relation with both our bubble sort and our merge sort. Right? So if we comment out our merge sort, we can see our bubble sort run again. If we comment out our bubble sort, we can see our merge sort run again. And at this size of data set, it's really difficult for us to tell which one is faster than another. And it looks like my internet's kind of hanging here. So at this, at these small data sets, both our merge set and our bubble sort algorithms are done pretty quickly. But what if we take this number set and we increase it by a lot? Right? Let's say we take and we, I was talking about that 10,000 number set earlier. Let's take that 10,000 number set and plop it in here. This is 10,000 values, all out of order. And so now it's my s.number set. And so let's run the merge sort on it. I'm going to go ahead and clear this out. Run the merge sort. And there we have all of our numbers sorted. Right, within like a second there. We got all the numbers sorted, and we can see they're all sorted if we look at the numbers here. 10,001, 10,003 versus, here we start out at 99,793. So our merge sort there was still pretty quick, even on a 10,000 number set. This demonstration is to show you how complexity scales. And so what I want you to get out of all of this is not necessarily just how exactly a merge sort works, although we've pretty much discussed that as well. Although if you're having trouble kind of wrapping your mind around it, it's okay. Right? What I want you to get out of this is less how exactly this merge sort works, and more the idea of the impact of complexity, especially when we go to scale. Because we said complexity scales relatively. So O of n times log n versus O of n squared scales relatively based on the size of the data. So the larger the data set, the more time it takes. So now I've commented out the merge sort. I have the bubble sort here to run, and I'm going to run it. And I'm going to keep talking to you while this runs, because it takes a couple minutes, right? It takes a couple minutes to run the bubble sort at scale with 10,000 numbers in the set. I mean, we saw the merge sort work, right? And the merge sort came up within a second there. Okay, there our bubble sort finally got there. And just to prove to you that wasn't a fluke, right? We'll clear this out. We'll do it again. Right? And we'll see that the bubble sort takes forever when we get it at scale. And so again, like the big things that I want you to get out of this module isn't necessarily that you know how to write more efficient code. But what I want you all to be able to do is to be able to look at your code and have an understanding of how efficient or inefficient that code is based on what you've written. There, my bubble sort finally ran there. And just to, prove the point again, let's go ahead and comment out the bubble sort and run the merge sort. Merge sort's done within a second. Quick, right? If I clear out my console, run it again, we see, boom, quick, done. Right? So again, what I want you all to get out of this isn't necessarily, like you're not going to necessarily know how to do something more efficiently just based on this. Right? That's going to come with time, that's going to come with experience, that's going to come with, just coding more. What I want you all to get out of this module is the idea that based on what you do, different things have different impacts on your code. And I want you to be able to look at the code and understand especially how it would be impacted at scale based on the code you've written. And so that's the whole idea that we get out of this module. And we see a beautiful example of that here. And I mean, this isn't even the most efficient sorting algorithm either, right? Like there are other sorting algorithms which you'll research. Like one, for example, is a radix sort. A radix sort is super fast. So if we were to make the set even larger, if we were to go to 1,000 or 1,000,000, we might see our merge sort bog down like our bubble sort is bogging down here on 10,000 items, but our radix sort will tear right through it. Right? But as we also saw, right, when our set was small, it didn't really matter. Right? So as long as you have control over your set, you know how small it's going to be, it doesn't really matter how you approach the problem because, with modern computing power, right? That was one of the concepts we talked about last week as well, the idea of complexity versus performance. With the performance ability of modern computers, even something that is very complex with a small data set can be handled quite well. Right? However, it's when we scale that performance is impacted by complexity a large deal, which is what we're seeing here in our example of using the bubble sort versus the merge sort. And so with that, that's all that I have for you for today. That is the last live class of the semester. I want to thank you for watching. I want to thank you for watching throughout the semester. I hope you all got something valuable out of it. We'll have our kind of drop-in time next week if you're having issues with your final project code. We'll hang out and chat with the music playing for just a minute, just in case anybody who's here with me live has any questions. Thank you for watching. We'll see you next time.